All right, so previously we talked about DC power. Now we're going to start talking about AC power, which is power in AC circuits, and how do we analyze it. One way to analyze the power in AC circuits is to analyze the instantaneous power, which is basically the power at any given time. So if we're looking at this plot here, this is I've plotted the voltage and the current basically already for a circuit, but let's see how we would get there. If I had this circuit here, basically let's go with something very similar to what we had previously. Let's just make this V of t. This is my R. Let's make it a 1 kilo ohm resistor, and let's just call this current here. Oops. We'll just call this I of t, and then of course the voltage across. We'll call that V of t. Actually, let's call this one Vs of t, just to stay consistent. Vs of t. Okay, so we've got some source that's going to put some voltage across my resistor here. Let's let Vs of t equal 10 times the sine of omega t volts. Okay, if that's the case, 10 sine of omega t volts across a 1K resistor is basically just going to be, my I of t is going to be Vs of t divided by R. So it would basically just be I of t is going to be 10 divided by 1K, or I can just say 10 times the sine of omega t milliamps, right? So that's my voltage and that's my current. And if I want to determine the instantaneous power for this circuit, the instantaneous power dissipated by my resistor, basically the power, the power dissipated at any instant in time, I can do that by taking the product of the current and the voltage, exactly like I did last time, except instead in the DC case, these are constant values because it's a DC circuit. In the AC case, these are functions of time. Okay, so we're going to have to do a little bit more math to determine the power as a function of time, which is basically what we're after. So let's go ahead and do that. My power as a function of time would be V of t, which is going to be 10 sine of omega t volts, multiplied by my current, which is going to be 10 sine of omega t milliamps. And so pretty quickly, you should probably be able to see that this is going to be equal to 100 times the sine squared of omega t milliwatts, right? Well, this is not a very satisfying place to be in, because if we wanted to do any math with this, we'd probably have to, this is fine. There's nothing wrong with this. This is correct. But we probably would have to use that same trig identity that we used a few slides ago to get that sine squared out of there. So let's grab that trig identity and just bring it over there with us. We'll go back. This is a very useful trig identity. We actually find ourselves using it quite often. So this is just a trig identity that I'll put here. And so we can replace that sine squared with a 1/2 times 1 minus the cosine of 2 omega t milliwatts. And the 1/2 can pop out, and my final value, or my final expression here, would be 50 times 1 minus the cosine of 2 omega t milliwatts, and that's going to be my power expression, okay, my instantaneous power expression. So if I plug in a value for t here, obviously this function is still a function of omega. I didn't pick a frequency here, but if we were to just let f equal some value, let's just say 1 kilohertz, of course we know that omega just goes to 2 pi times 1 kilohertz, right? And so we could plug that value in, we can plug in a value of time, and we could determine the value of the power being dissipated at a particular instant in time. Okay, so let's just grab this and pull it over, because I actually plotted this on the next page here. My purple trace here would be, let's make this purple just for that reason. My purple trace here is the power. That is the function that I just basically derived, function of t. And so we can see that when my voltage and my current reach a maximum, right? They're at a maximum, my power is at a maximum. When my voltage and my current are at 0, my power is at 0. What happens when my voltage and my current reach a negative maximum? Well, because the power is the product of current and voltage, when the voltage and the current are both negative, the product is positive, so I get another maximum. And so you see that in this case, let me actually grab the circuit itself too so that we have that over there as well. Geez, come on, copy. What the heck is it doing? There we go. Sorry about that. So if I have this circuit here, even though there's times where the voltage and the current are negative, the power doesn't go negative because the power is the product of the current and the voltage. And because for a resistor, we have we have our current and our voltage always in phase with one another, right? The phase angle here is 0. There's no phase, there's no phi present in this function. It's not dependent on the phase whatsoever. It's strictly dependent upon time, and the power is always positive. You can see that it stays above the x-axis here in the positive region, and that's really important to note, that the power in the case where the load is purely resistive is always positive, because when we get further along in our power analysis, what we're going to see pretty soon, not just yet, but maybe in a few slides, is that sometimes the power will go negative as this phase shift between the voltage and the current becomes non-zero, right? You can see pretty clearly here that the voltage and the current are in phase, right? They peak at the same time, they hit 0 at the same time, they reach their negative peaks at the same time, they're perfectly in phase. And so as a result, the power is always positive, right? Again, when the voltage and the current are 0, the power is 0. When the voltage and the current are maximum, the power is maximum. And then when the voltage and the current are negative maximums right here, I guess you could call them minimums, but they're really negative maximums, we get a maximum for power as well. And that right there is the proof that my power signal is 2 times the frequency of my original signal, right? My original signals were V of t was 10 times the sine of omega t. That's the frequency of basically omega. This current that we found was 10 times the sine of omega t milliamps, also at a frequency of omega. And out of the trig identity pops a 2, which can be basically viewed as a doubling in frequency. And you can see that 1 full period for my voltage is here, right? That's 1 full period. And by that time, my power has already undergone 2 full periods. Right, so that's showing that frequency doubles, and we can kind of see that graphically when we analyze what's going on. When the voltage and the current are both negative, the power is also positive, and so at a rate of 2 times the frequency of the voltage and the current, our instantaneous power is given. Okay, so I'm going to go ahead and end this video again. Maybe I mentioned it already, but maybe I didn't. Typically, instantaneous power is not of much interest to us in AC circuits. It doesn't really matter what the power is at a particular instant in time. We typically want to view the power over long ranges of time. And so what we're more interested in is the average power, which we've already seen now how to take the average value of a signal. So if we can calculate the average value of this power that we just found, we can very easily determine the average value of this signal, which would be the average power dissipated by this resistor, which is a much more useful metric in power analysis than instantaneous power. Okay, so I'm going to go ahead and end this video, and in the next video, we're going to start talking about average power.